The correct answer is that it adopts the shape of its container. The problem is that the quiz that's in the video accidentally has the wrong answer selected, and it's expecting you to answer that making the measurement is as undefined as dividing by 0, which doesn't make any sense. Now, there are 2 questions in a row, one about gases, the other about liquids. The gas one is fine. The liquids one, the second one, you have to put the wrong answer in on that. I apologize for this problem. I am going to be, for the future videos I'm working on, I'm going to be introducing extra error checking on myself to ensure that I don't do these kinds of mistakes in the future. Okay, Friday, homework 2 is due. There are 3 Newton-Alta components and 1 supplementary question. And a week from yesterday, the first group activity should be due. So all the groups have been assigned. You should be able to see the group discussion boards now and start the conversation with your group members to figure out the logistics of when you're going to work on those activities. My office hours are posted on Piazza now. There are direct links to the Zoom chat room for those office hours. Please take advantage of them. It's an opportunity for you to one-on-one ask me any questions that you're having about the material, and I will be happy to go through anything you would like me to go through. I have yet to have anybody show up, so there's not going to be much of a wait if you show up. So please take advantage of this as a resource for you. Do we have any logistical questions or issues that we need to talk about before we get going? Nope. Okay. So the muddiest point list that we have is pretty short today, so we will have to, I hope you guys came with some questions to talk about. So one of the questions was, how can you tell when you're supposed to use the face-centered cubic, or it said BBC, but I think they mean BCC, the body-centered cubic equations? Well, you'll be told which one you want to be using. You're not going to magically know which crystal structure is the one that you're going to be dealing with. You'll have to be told this particular compound is body-centered cubic, and so then that's when you use that one. There was a question about from the video when we were determining the packing efficiency. About how the face diagonal and the body diagonal can both be calculated with 4R. So let's take a quick look at that. I'm going to switch to the PC here. Share the screen. Okay. So if we look at the face-centered cubic lattice, there are 2 ways to look at this. Let's come down. Seriously, stop it. Here we go. Okay. This is one way to visualize it, where you put little dots at each place where you're going to have an atom. Now, this method of representing the face-centered cubic structure doesn't tell you directly what is in contact with what. So a better representation when you're trying to figure that aspect out is going to be one of these more space-filling kinds of diagrams. Let's see if we can find one. And did I bring... I may not have brought the PowerPoint files that I had. So I'm just going to have to hope that I can find one down here that actually shows this. Oh, here we go. That one's good. All right. So looking at this picture right here, we can see that in a face-centered cubic structure, the points of contact between the spheres are here on the face itself, okay? So in the face-centered, that means that in the face-centered cubic structure, the distance from here to here is 1 radius. The distance from here to here is a radius. The distance from here to here is a radius. And the distance from here to here is a radius. So the distance along this diagonal is 4r. Okay. Now, if we look at the body-centered cubic, seriously. If we look at the body-centered cubic structure, this is a pretty good representation of it. We can see that the points of contact are along the body diagonal, going from this corner to this corner. Okay, so you have a radius in the body diagonal from this corner to the point of contact. You have 2 radii going all the way across the central atom, and then you have 1 radius going from here to the corner. So it is not that the body diagonal and the face diagonal are always 4r in every case. It's that in the face-centered cubic structure, the face diagonal is 4r. And in the body-centered cubic case, the body diagonal is 4r. Okay, does that make some sense? Okay, so in all of these cases, I strongly recommend against just trying to memorize formulas. Okay. Instead, think about the geometric structure, and the information basically just falls in your lap as a result. Okay, so switch here, back to that. Okay, so how do you count the faces in a unit cell? Where are my pens? Here we go. How do you count the faces in a unit cell? Well, so the general idea here, since we are primarily dealing with cubic unit cells, what you are doing is counting the faces of a cube. Okay, so think of it like a 6-sided die that you could roll. So top, bottom, front, back, left, right. So 6 faces. That's really all that there is to that aspect. Okay, and then in water, do the hydrogen atoms ever separate from the oxygen atoms throughout the phase change? So we need to be very careful about how we are phrasing that. So if we have a water molecule that looks like this, that water molecule in the solid or liquid phase is hydrogen bonded to other water molecules. Oops, that should be a dotted line there. So you have this network of water molecules that are all held to each other by intermolecular attractions. In this case, we are explicitly showing the hydrogen bonds. When we go from this state to a gas phase, the molecules separate from each other, but the atoms within a molecule do not separate. So in the gas phase, you will have molecules of water that are still covalently bound together, but they are no longer attached, the molecules are no longer attached to each other through the hydrogen bonds. It's really interesting. There's, back in the 80s, there was an advertisement in the Land's End catalog for a particular kind of outerwear, a rain slicker or something. And it's advertised it as separating the H's from the O's in water to prevent the water from sticking to you. And of course, if you do that, you're making hydrogen gas and oxygen gas, which would be an explosive combination. So on an exam I gave back in the 90s, I think it was, I showed a picture of this advertisement and had the students analyze, tell me what's wrong with this ad from a chemistry perspective. So this is a common misconception about what goes on when something goes into the vapor phase. A common misconception is that you are breaking the atoms away from each other in the covalent bonds, and that is not the case. Okay. That is actually the full list of muddiest points that were available on Piazza. So let us open this to everybody for any questions anybody has on any of the material. I will be watching the chat here as well as anybody here that's live. Yes?
So why is the simple cubic only 2R?
Why is the simple cubic only 2R? Okay, excellent question. Let us take, let's take a look here. So again, if we look at the space filling diagram, it will hopefully become clear. Simple cubic unit cell. So images, that one's pretty good right here. So if we look here, we see that the point of contact between two adjacent spheres is right here along an edge. So 1R, 2R. Okay. Let me stop share so I can see the chat over here. Are there any other questions? Or just general, I don't get it on a particular topic. I'm happy to just riff on something if you guys would like a reintroduction to some of the material. Would you need to calculate, from the chat, would you need to calculate the diagonal for the simple cubic? Well, let's see. So if we come back here to this structure right here, the reason that we use the diagonals for the face-centered cubic and the body-centered cubic is that that's our only way to make the connection between the radius of the atom and the volume of the sphere. Okay, so in order to, volume of the sphere, excuse me, the volume of the cube of the unit cell. In order to know the volume of the cube, you have to have some kind of relationship between the radius of the atom and the edge length of the cube, because the cube is going to be edge length cubed as the volume of it. So in the case of simple cubic, you can get the edge length as being 2R directly. And so you don't need to go to a diagonal in order to find that information. If instead we are looking at, say, the body-centered cubic, Hey, look, it's the same figure from our textbook. All right. If we look at the body-centered cubic, where we have 4r going from opposite corners, then you can use the Pythagorean theorem to get from the body-centered cubic to the body diagonal to a face diagonal, and then use the Pythagorean theorem again to get from the face diagonal to an edge. So you only need to use the diagonals when the diagonals are what gives you the relationship between r and a quantity related to the size of the unit cell. In the case of simple cubic, you don't need to. Okay. So also from the chat, if the question gives us the edge length, we do not need to worry about the face length. By face length, I assume that you are meaning the face diagonal. That's correct. You would not need to know the face diagonal for anything in that case. Yes?
I'm still confused about the difference between the face diagonal and the body.
Okay, so visualizing what they mean on a cube, is that what you're talking about? Okay, so let me see, I may be able to do this a little bit differently. Okay, so trying to think the best way to make a cube here. Okay. A jury-rigged cube. Okay. So the face diagonal is going to be looking at one of the faces and going from this finger down to this finger down here. Okay. The body diagonal is going from a corner to the corner that is exactly opposite all the way across. Does that help clear it up? Okay. Were you able to see that on the chat? Was that, okay, cool. What else can we try to clear up? Yes?
Sorry, so does that mean that the face diagonal will usually be the same amount like at the bottom?
Does that mean that the face diagonal will usually be the same length as the body diagonal? No. So if we, let's look over here. So if we look at the face diagonal, well, let's call the edge length here S because it's a side, okay? And we will draw the face diagonal. So blue here is the face diagonal. We also have an S here. And this is a right triangle. So this length here is going to be the square root of s squared plus s squared. That's from the Pythagorean theorem. So this means that this then is going to be the square root of 2 times s. Right? Now, if we look at the body diagonal, we've got another color here. There we go. All right, we'll do the body diagonal. So let's do that diagonal there. Okay. So one of the edges here is S. The other edge is the square root of 2s, right? So using the Pythagorean theorem, s squared plus square root of 2s quantity squared is going to equal our body diagonal squared. So we'll call that b. So this becomes s squared plus 2s squared equals b squared. 3s squared equals b squared. And so b equals the square root of 3s. Okay. So for every, and this is just a geometry of a cube. This has nothing to do with unit cells or anything like this. This is just the relationship between the sides, the face diagonals, and the body diagonals. And all you need for that, to figure that out, is the Pythagorean theorem. Okay. Anything else? So we're focusing a lot right here on the unit cells and lattices and such for crystalline substances. We also have all of the phase diagram stuff, cooling curves and heating curves. And we have the properties of solids video that was talking about things like ionic compounds and their brittleness versus metallic compounds and their malleability and electrical conductivity and so on. So think about all of those. It looks like we have someone here in the chat saying, still confused about hexagonal close packing. Okay, so let us look here at the textbook. Okay, so I'm not sharing the screen, am I? Let me start by doing a little demonstration here. I'm going to switch this back to the document camera. On Zoom, are you seeing the? Yeah, you're seeing the. Okay. So let's take here just a bunch of pennies. Okay. It's important that you can do this with any size coin you want, but it's important that they are all the same size. So you can't mix in quarters and dimes and that sort of thing. What we're going to do is now we're going to compact these just by pushing on one side here. Okay. Now, what do you notice happened very naturally right there? If I do it right. You see how this has arranged itself. That glare is actually not that great, is it? The way this has naturally arranged itself is sort of this triangular pattern. Okay, and in fact, if you look a little bit larger, you see a hexagonal arrangement here. Right? That's simply because this is the arrangement of circles that when they're in a plane and you're trying to pack them together, that minimizes the free space. It maximizes the places where they're touching. Spheres will do exactly the same thing. So if we look at spheres that pack in a given layer, and here we're looking at it from the top, you can see that this arrangement of the spheres is identical to what we just saw in the pennies that I was showing you. Okay. Now, when you look at this structure, you can see that there are little divots at sort of triangular places where the triangles come together. So there's a divot here, there's a divot here, a divot here, a divot here, and so on. Okay. So when you are creating the next layer and are putting the next layer of spheres down, they're going to naturally fall into those little divots. But they're not going to fall into every one because two adjacent ones are too close together, and and you just can't fit two spheres that close. It'll only the spheres will only go over half of them. Okay. When you do that, then when you bring up the third layer, you again have a choice of putting the next layer of spheres over what were the set of holes in the first layer that you didn't cover with the second layer, or you can put them right over the ones where the first layer was. So that's why we call one of these packings ABC, because they're in three different places. And the other kind of packing is ABAB, because we place one layer, we place a second layer. The third layer is going to be directly over the first layer in the other way to do it. Okay, so ABAB, ABC, ABC. Okay, it's labeling. I was pointing at them differently. I was counting from the bottom, but hopefully you get the idea. Yes. So hexagonal is actually the one where it's ABAB. Cubic close packed is the one that's ABC, ABC. Okay. So in one of the videos, content videos, I'm going to see if I can get there. My channel. So okay, so we're going to come forward to this part right here. Okay, I'm going to go to full screen. So what we have here is a face-centered cubic arrangement. And what we are going to do is rotate how we're looking at it. Okay, so, all right, so we had a face-centered cubic structure extended to multiple unit cells. We're going to rotate it up this way, and we're going to now recolor it so that we can see the layers. Okay, and then take off the top view so that we can see what we're looking at. So looking at when we stick this unit cell on its diagonal, on its body diagonal, then we can see that we end up with layers that look exactly like what we were just describing with the ABC arrangement. So because the unit cell in this case is cubic, this because it was face-centered cubic structure, this is known as cubic closest packing. Okay. The other one, so this here is showing what I described a minute ago. So bring in a second layer, and then we have a choice about how to bring in the third layer. So there we are doing ABC, and so these the blue layer is going over the holes that were present in both of the first two layers. Whereas on the right-hand side, we're bringing it in directly over the green atoms. So the left-hand side is the cubic close packing, or face-centered cubic, which end up meaning the same thing, even though they're emphasizing different aspects of it. The right-hand side is hexagonal close packing, because when you break down what the unit cell looks like, it looks like this portion of a hexagon right here. Okay. We are not going to, I'm not going to have you do any calculations on the hexagonal closest packing. I'm not going to have you needing to determine edge lengths from it. And so we're not actually going to worry about demonstrating that it is hexagonal. I'm just pointing out that it is. Okay. Does that help? I think that was a question. Okay. All right. What else can we talk about? Yes?
Can you explain where octahedral holes happen versus tetrahedral holes?
Sure. So octahedral holes versus tetrahedral holes. So let me go back to screen sharing. Let us pull up okay, so what we mean by an octahedral hole or a tetrahedral hole is how many closest neighbors there would be to the center of that hole. So if we have a let's back up here. Suppose that we have a simple cubic structure. And we know from the simple cubic structure that there's a hole right in the middle of that simple cubic structure. If we put something into that spot, say a smaller ion, then the number of nearest neighbors is going to be 8. So that would end up being an octahedral hole. Now, if we have a, let's say a face-centered cubic structure, then dead center is going to be a hole, which is going to have 1, 2, 3, 4, 5, 6 nearest neighbors with the faces. So that's one we didn't even mention. That's a hexahedral hole. Let's see if we can see an example of a tetrahedral hole. So I guess they call that a cubic hole. So a tetrahedral hole would be, this isn't a very good picture. Let me see if I can find a better picture than that one. Okay. Okay, so if we have a face-centered cubic structure and we look at one of the corners of it, you see here that this is this front upper right corner. The hole in the middle of this has 4 adjacent nearest neighbors. So that would be a tetrahedral hole. Okay. What else can we talk about? Yes? How you would draw a phase diagram? Sure. So let us here. And let's talk through this together. So, first, what are the axes for a phase diagram? Yes. Temperature and pressure, right. So, which one are we going to put on which axis? Let's see here. I think we normally do temperature here and pressure here. Okay. Let's start by labeling some regions. At high temperature and low pressure, what is our phase going to be? What's our state of matter? Yes. Gas, correct. At low temperature and high pressure, what is our state going to be? Yes. Ice or solid. So if it doesn't have to be water that we're doing. So we'll call this solid. Okay. So we're going to have some kind of line that goes between solid and gas. It's going to, and that's going to be our sublimation or deposition line. It's going to reach a point where it's going to split and create the liquid region. So we'll have a line going like that, and then we'll have something coming up like this. So this will then be our liquid region. This continues on beyond the graph. This side here reaches an endpoint. Okay. What is this point called? Yes. The triple point. Because it is the location where all three phases are in equilibrium with each other. What is this point called? Yes, the critical point. Okay. Each line corresponds to two phases being in equilibrium with each other. Here is the equilibrium between solid and gas, and I already said that there is sublimation as you cross it in one direction and deposition as you cross it in the other direction. This line is the equilibrium between liquid and gas. What is the transition called when we go from liquid to gas? Yes. Vaporization or boiling. Yep. When we go from gas to liquid? Yes. Condensation. What about when we go from solid to liquid? Yeah. Melting. When we go from liquid to solid? Yeah. Freezing. Right. Okay. Up in this region up here, we have something that is neither liquid nor gas. It has some characteristics of both. This is called a supercritical fluid. Okay. And this is the case, this is what you have when there is enough kinetic energy in the system for the molecules to be able to escape their neighbors to be able to go into the gas phase, but there isn't room enough for them to do so because of the extreme pressure that they're under. So they're being held in place by the external pressure of the system, of whatever container they're in. And so, so what this means is that you can go from a liquid to a gas or vice versa by having a sample that starts out here, increase the temperature until you're into the supercritical fluid regime, decrease the pressure until you're into the gas regime, and then you can cool it down again, and you now have gone from liquid to gas without ever having proceeded through a phase transition. This is an extremely powerful approach for doing a variety of things. I've used it in my own research, or something similar in my own research, having to do with trying to make aerogels. So an aerogel is a substance, think of it kind of like the girder structure of a building. So it's mostly empty before you put any walls or floors in. So it's mostly empty space, in our case, air, but it has a little bit of solid that's making this sort of web-like superstructure that's part of it. These aerogels are extremely lightweight solids that are mostly empty space. Now the problem is, how do you make one? You have to make it by depositing the solid, and you usually deposit the solid from some kind of solution or some kind of fluid. But then if you just evaporate the liquid off, you get little capillary, you have capillaries between the little particles. And we've talked a little bit about surface tension, which is going to then pull, at the surface of the evaporating liquid is going to pull the edges of the particles together, and your giant girder structure then just collapses into a pile of metal without leaving you all the space inside that you wanted. So what you can do instead is deposit the stuff in solution, but you don't evaporate the fluid that you were using. You transition up to a supercritical fluid and then down to the gas phase, and you've never had a meniscus, you've never had a capillary. So there are no forces that bring it together, and you can be left behind with your aerogels. These are really cool substances. People use them so NASA uses them quite a bit. You might remember when they sent a probe out to sample the gas from the tail of a comet. Well, what they did was they opened a hatch, stuck out an aerogel, and the gas from the comet hit the aerogel, and because it's so open, the particles from the tail of the comet would go in there, stick to it, and they brought it back to Earth, and we actually have a researcher in the chemistry department, Michael Callahan, who studies this material that they brought back. And the whole approach is made possible by understanding phase diagrams. So did that help? I know I went off on a tangent. I apologize. Okay. So it says, there was some confusion about the supplemental question that I saw on Piazza. Can you clarify what you're asking for in the chat? While we're waiting for that clarification, does anybody else have other questions? Okay, so she doesn't need the answer then to that. Nothing. Everybody's feeling confident in this material? So let's talk through some ideas here. I'm going to share here. Okay, let us suppose that let's suppose you are told that an ionic compound has a structure where the anions form a simple cubic lattice, and the cations fit into the octahedral holes inside the simple cube. How could you find out the largest cation that could fit without expanding the lattice corners? And let's assume that you have been given the radius of the anion. Yes?
You use that to find the base diagonal using the Pythagorean theorem, and then use that to find the body diagonal, also using the Pythagorean theorem, and then minus the radius.
Right. So you use the known radius of the anion to give you the side length, the edge length. You use the Pythagorean theorem to find the face diagonal size. You then use the Pythagorean theorem again to find the body diagonal length. And we already did that a few minutes ago, and we determined that that was square root of 3 times the side. So square root of 3 times 2r. You then subtract off 2 of the radii, because this is now, you have the anion radius that's along that body diagonal. And what you have left is the largest diameter of a sphere that can fit inside it. So you divide that by 2 to get the largest radius of the cation that could fit inside it. Okay. So this kind of problem is why I am suggesting do not go in and try to memorize the various equations for face-centered cubic, body-centered cubic, any of these sorts of things. Because the interesting questions to ask are going to be taking the structure you have, and then what extra information does that give you? So maybe instead then I might say, well, what about if the cation is going to be fitting in the center of the face rather than in the center of the in the octahedral hole? Okay. Well, do you need to memorize that equation too, or should you approach it by using your understanding of the geometry and figuring out the formula from it? So that's why I'm suggesting that it's visualize the geometry and think about how the parts relate to each other rather than memorizing stuff. Okay. So there was a Piazza post about packing efficiency, and so which I responded to in class yesterday. But if we don't have other questions, there was enough confusion about that that it might be worth going over that again if you would like me to. Would people like me to do that? Okay. So the general idea, let me switch over here. The general idea is that if we imagine our unit cell with some spheres in it, and I'm just going to draw the simple cubic because the calculations are a little easier. Okay, so if we think about this packing of the spheres, there's clearly space in between them. So think about this like taking a bunch of marbles, pouring them into a beaker, and then filling the extra space in between them with water. Okay? So packing efficiency is what fraction of the resulting mixture is marble compared to what fraction is water. That's what we're trying to determine. So the general idea for doing this is, since the unit cell is the thing that's repeated all the way through the entire substance, if we find the ratio in the unit cell, then that's going to be the same as the ratio over a bulk sample. Okay, so what we want to do is have the volume taken up by the spheres divided by the volume of the total unit cell, right? And so if the volume of the spheres is half the volume of the total unit cell, then you would get 0.5 here. That's the general idea of what we're trying to do. So in this case, we have an edge length that is 2r. If that is the case, what is the volume of the total unit cell? Yes. 2r the quantity cubed. Right. Now, what is the volume of a sphere of radius r? Anybody remember that one? Okay, 4/3 pi r cubed. Okay, so that's the volume of one sphere. How many spheres are there in this unit cell? 1. So there are 8 spheres, 1 at each corner, but only 1/8 of each sphere is in that cell. So 8 times 1/8 gives us 1 whole sphere inside the unit cell. So we now take 4/3 pi r cubed, and this is going to give us our packing efficiency. So the r's cancel. And so we have 4 pi over 3 times 8, because 2 cubed is 8. 4 cancels, this becomes a 2. So we get pi over 6. And so what is pi over 6? If somebody has a calculator.
.526.
0.526. So 52.6% of the unit cell is taken up by the spheres. We have a packing efficiency of 0.526. General idea makes some sense? Okay. Anything else? Well, if nobody has any questions, I'm happy to let you guys go early if you wish. Entirely your call. All right. Thank you. Oh, okay. I got a question from the chat about explaining the importance of coordination number. Okay, so the general idea of coordination number is just how many nearest neighbors do you have? There are some types of interactions or reactions that happen between nearest neighbors. And so knowing how many nearest neighbors you have tells you how many of those interactions you're going to be having. So one type of example of this is that because water's interactions are largely hydrogen bonding, and because it has 2 donors and 2 acceptors, that suggests that water is probably going to exist in a crystal structure where its coordination number is 4, because it's going to have a tetrahedral arrangement of its nearest neighbor interactions. Okay, so that's an example of how you can use some insight from coordination number to tell you what the structure is likely to be. Okay. All right. Thank you all.